Okay, we're going to do another example of a direct proof. In this case, we're going to do a proof about composite numbers rather than even or odd. These ones tend to be slightly trickier, but it's not much. So let's take a look at an example. First of all, as always, I want to remind you of what are the steps to doing a direct proof. Well, first we're going to express the statement as a universal conditional statement. Right? And then we want to suppose this first part of the statement. And then we want to deduce the second part of the statement. Okay, so let's get at this example. Here we have a question. So I'm not saying prove that this is true. I'm asking, is it true? Is it true that for all m and n in the integers, if m is greater than n, which is greater than 0, right, so n is greater than 0, so n might be 5, and then m must be bigger than 5, so say 7. Is it true that m squared minus n squared is composite? All right, well, this one, it's not really clear. Is it true that it's always the case? Well, I don't know. You could try some examples, and you may learn something. What I'm going to do is I'm going to try to prove it's true, and then see what happens. Right? See if I can prove it true if I run into some kind of a mistake. And I'll give you a hint right now. This actually is not true. If you do some examples, you'll see that. But what I want to do is illustrate what if you try to prove something true that isn't true. Right? What's going to happen? So we're going to try to prove it true. And first step is I'm going to notice that the question is actually already in the correct format. We have for all m and n in the integers, we have our if statement, and we have our then statement. All right, so I'm not going to bother rewriting this. I'm going to just say that step 1 has already been completed. It is in the form of a universal conditional statement. So if it's in the correct form, what do we want to do? We want to start by supposing this first part of the statement. So, proof. Suppose m and n are any integers such that m is greater than n is greater than 0. So what I'm doing is I'm not putting any constraints on m and n other than those given by the problem. Okay, so that is step 2. I guess I was using blue for this. That's step 2. Now, what's our goal? Our goal is this latter part. We want to show that m squared minus n squared is composite. All right, that's our goal. Well, if you recall, what is the definition of composite? So I'm going to rewrite that as part of the proof. You don't have to, but in other words, So we need to show that, remember, there's two parts to being composite. One, that m squared minus n squared is greater than 1. That's one of the requirements. And because composite numbers are always greater than 1. And that m squared plus n squared is equal to the product of two numbers, r and s, where r and s are integers, and that r is between 1 and our total, and that s is between 1 and our total. Right? Because every term, including m squared plus n squared, is always going to have two factors, 1 times itself. Right? So what we're doing is to show that it's composite, we need to show that there are additional factors in between those values. Okay, so how am I going to do this? Well, this looks a little tricky, right? One thing I can notice is I can show this first part without too much difficulty, right? So I can say that since m is greater than n is greater than 0, the squared values, what that means is that m is greater than or equal to n plus 1. All right, it could be bigger. And so the m is at least 2. Actually, n has to be at least 1, so m is at least 2. So if you put this together, there's always going to be a gap of at least 1 between them. If we square the bigger number, so m squared is going to be greater than or equal to n plus 1 squared, which is going to be greater than n squared. Right? Because remember, n is at least 1, which means n plus 1 is at least 2. And so the n squared, this is always going to be bigger than n squared. So if m squared is bigger than n squared, then that means their difference will be greater than 1. Right? It won't be equal to 1 because m squared is going to be at least 2. So the smallest possible difference would be if this is 2 squared minus 1 squared, which is 4 minus 1, which will be 3. So 3 is always greater than 1. This part isn't a proof. This is just a little bit of an explanation. Right? You cannot do proofs by examples like that. This is an illustration, not part of the proof. This is our proof here. In fact, I would argue that to somebody in discrete math who's taken calculus before, we may not even have to lay that out. It may just be obvious enough. Okay. So I'm going to move to the next page because I'm running out of space here. Let me see. Another way of writing this, I'm going to just scribble one more little, maybe better proof down here. I'm going to say that notice, actually, this is, you could think of this as a little lemma. M squared minus n squared is greater than 1. And the proof of this lemma is that since m is greater than n, I'm going to, instead of saying that m is greater than or equal to n plus 1, so the greater than or equal can be a little hard to think about. Inequalities are hard. So instead I'm going to let m equal n plus a, where a is an integer and a is greater than 0. So right now I'm doing something called existential instantiation. I'm saying I know there's some difference, there's some number that when added to n gives me m, and I'm going to name that number a. So this is an example of existential instantiation. I haven't finished my proof though. We're going to have to go on the next slide for that. Let's try to do it here. So m squared equals n plus a squared, which will be, okay, let's scribble this out. N plus a times n plus a equals n squared plus na plus na plus a squared equals n squared plus 2na plus a squared. And since we know that a is greater than 0, this will be positive. And thus, so this is n squared plus 2na plus a squared, which will be greater than n squared. Okay. Which means, really running out of space here. So m squared minus n squared will in fact equal 2na plus a squared, which is greater than 1. Okay, so that's my little lemma. We're going to move to the next page. So we've demonstrated, let me scribble this out here. So we've shown m squared minus n squared is greater than 1. And now what we need to show is this part. All right, there's the two parts. We've shown the first part. Now we have to show that there are two integers, r and s, that when multiplied together give m squared plus n squared. And those r and s are between 1 and m squared plus n squared. Okay. So we've already been part of the way. So since m is greater than n, I'm going to let m equal n plus a. So we've already done this, where a is an integer and a is greater than 0. So what does this mean? Let's take a look at n squared, or m squared minus n squared again. We've shown that this is equal to n, oh, wait a second, m minus n squared minus n squared. So this is equal to m squared plus 2na plus a squared minus n squared, because we showed that this was m squared. Or another way of writing this is that, excuse me, I am sorry, this should be an n, is that this is equal to n plus a squared minus n squared. Okay, I'm regressing. We need this other one. N squared plus 2 na plus a squared minus n squared. Well, what do we see here? We see we have 2 n squareds, so we can cancel them out. And we're left with 2na plus a squared. What can we do there? Well, I can factor out an a. Right, so now I have two factors. Can we call this one an R and this one an S? Well, it seems like that's fitting our definition. Recall our definition is we need two integers, R and S, that when multiplied together give me m squared plus n squared. Well, R times S gives m squared minus n squared. So this looks like it works on the surface, except we still need to prove this part, that R is greater than 1 and less than m squared plus n squared, and S is the same. So let's take a look. Let's look at R. Can we show that R is between 1 and m squared minus n squared? No, we can't. Because if you recall, the definition of A said that A was greater than 0. It does not say that A is greater than 1. And that's the requirement here, is that A be greater than A, or R, which is the same thing, is greater than 1. So this is where our proof falls apart. I told you that this is a false statement, right? So this is false, or no, because it's a question. And the reason, even if we try to prove it correct, we can get pretty far, but it's going to fall apart at some point. And it's going to fall apart based on the definition of composite, where that definition says that R has to be greater than 1, and we know that R could be 1. So this isn't going to work. And again, the justification for all these steps was just we're using algebra. So, what if A, which equals R, is equal to 1? Right? It's not guaranteed that A will be greater than 1. So, our proof falls apart. So this is what happens if you try to prove something true that isn't true, is at some point in your proof, you're going to get stuck. And this is a little bit of a subtle place to get stuck at, because this looks an awful lot like two factors. And this is why it's so important to go back to the definition and why we have these formal definitions. Because to show that this m squared minus n squared is composite, we have to go to the definition of composite and be nitpicky about the fact that this doesn't in fact fit. Okay, so I thought I had one more page to fix it. I guess not. So let me erase this. I also thought I had the solutions typed up for this one, but I guess I don't. Okay, so that didn't work. Let's suppose it's false and see if we can prove that. And we're going to be able to. We can do a proof by counterexample. Right, so we have a universal statement. So if I can find an example where this isn't true, then my entire proof is false. Proof by counterexample. I'm going to let m equal 3 and n equal 2. There are many proofs by counterexample. In fact, it may be that all values are counterexamples. I haven't played with it. Then m squared minus n squared is going to be 3 squared minus 2 squared, which is 9 minus 4, which is 5, which is not composite. This is prime. Therefore, since there exists an m and an n in the integers such that m is greater than n is greater than 0, and m squared minus n squared is not composite, the statement is false. And notice a proof by counterexample is still a proof, which means we want to explain ourselves. It is a story. We want to say, lead the reader by the hand and say, why is this statement false? Well, it's because of this.